The topic of the video today is a use case for VASI interfaces and associated VRFs where we can completely isolate traffic for various customers, IKEv2 Route Based VPN tunnel. The idea is I want to be able to assign NAT IP space for various customers and be able to have VPN tunnels with customers that have the exact same overlapping IP networks. So basically what's going on is creating two different set of left and right VRFs that are associated with the VASI left and right interfaces. And again, this is route based, so there's a tunnel interface. So on this VRF's router, physical interface G1 is going back to our core router, we'll see in a minute. Physical interface G2, this is what's facing the ISP, public internet customers. And so basically what I'm going to do is I'm going to assign a 10.77.0.0/24 network. That's going to be NAT space. I'm going to route that and then take that space and split it up into some /29s for what we'll see as a customer 10, 20, and 30. And then basically what's going on is the NAT translation is happening between the VASI right interface and the tunnel interface. So IP NAT outside for the tunnel interface, IP NAT inside for the VASI right interface. And so the idea here in this example is I want to be able to say, I want to go to send traffic to 10.77.0.2. And then I want that to translate to the native IP of 10.254.254.2, which is on the customer network. So basically, the 10 here is referencing customer 10. So we've got VRF 10 left, VRF 10 right, tunnel interface 10, VASI left 10, VASI right 10. So that these VRFs are totally isolating the traffic to that particular customer. So that's the general idea. And in the lab here, I've already got 3 different customers set up, 10, 20, 30, as I mentioned. These are all route-based IKEv2 tunnels. And each one of these Linux hosts all have the same IP address. So they all have 10.254.254.2. So that's the customer 10 Linux. Same thing on this one, same IP address. And customer 30, same IP address. On the headquarters Linux, the IP is 150.2.3.248. So we'll see how that all works. And the configuration for the entire lab will be linked in the description. That way you can see the configuration for these are iOS, and then this is a ASA. So the ISP router is pretty simple. It's just basically got OSPF running. The VRF's router is on the 20.30.40.2, and then customer 10, 20, and 30 are the 30, 40, and 50. And so OSPF is running between the ISP, VRFs, and these various customers just to simulate and like an internet connection at ISP, so that we can have true IPsec tunnel going across those IKEv2. So I'm going to start on the core router. And actually need to, I didn't have the core router started. So VRFs is also not started. Whoops. So I'm not going to edit this video. So wait for these to load up. So while that's doing, I can cover the configuration. So the ASA G00 outside interface with the public IP of 50.60.70.1, which is what you see linked here on the ISP. Inside interface 10.254.254.1/29 network. That's what the customer 30 Linux is connected to. So you can see its default gateway is 10.254.254.1. We've got the crypto configuration, GCM 256, phase 2, phase 1, just one phase 1 policy. Route based VPN, so tunnel interface here. The IPsec profile is referenced in the tunnel interface. And then in there, that's when you're specifying what phase 2 or IPsec proposal that's going on there. Standard tunnel group configuration for any VPN tunnel, or LAN to LAN on an ASA. We're saying I want to route to the 150.2.3.0 network and send that out the tunnel interface. The OSPF setup. I've got my object networks. So this is the remote network. So I'm on the far right side, the customer 30 on the ASA. Ultimately, I want to get to the HQ Linux, which is on that 150.2.3.0 network. Local IP address for the Linux box, and then a no-NAT statement so that the packet doesn't have any translation. Source IP is remains original when it's going to go across the tunnel. So let's see if either one of these have booted up yet. Core router has. So I'll go to that. So again, this core router is just booted up, no configuration. The G01 is kind of like the LAN subnet for the HQ Linux 150.2.3.1/24 network. The 00 is what's facing the VRF's router, 172.16.01 on a /30 network. And then this is the key here, as I'm defining a 10.77.0.0/24 network with the next hop of the VRF's G1. So basically this is the NAT space that I want to use for various customers. So this is a /24 network, and customer 10, 20, and 30 are going to have a /20, each going to have its own /29 from this range. So that's the key here, is I want to be able to communicate with these various customer networks over VPN tunnels, but they have overlapping IP space. In fact, they have the exact IP space. And by doing this NATing setup, I can communicate with those on an isolated basis based on the NAT IPs. And then again, the NAT translation is happening in the VRF 10 write area between the VASI write and the tunnel interface. And I'll get to that in a minute. but we'll throw that route in there. So if I do show IP route for the core router, for what's effectively the LAN segment, we have that 150.2.3.0/24. The direct link to the VRF's router on this /30 network, and then this NAT space that I'm routing. I'm saying if I want to get to this 10.77.0.0/24, send it to the VRF's router. So really this is just the beginning of how I'm able to communicate with the different customers on overlapping IP space using NAT translation. Okay, so the VRF's router is booted up. Okay. So the G1, that's the link to the core router I've been talking about. G2 is the link to the ISP. Going to define the VRFs. There's no route distinguishers because I don't need to exchange any routes. Loopback and the OSPF configuration. This is just there so I can just have routing to these customers, so I can do a true route-based IPsec tunnel. We'll go ahead and define the VASI left 10, VASI right 10. And so the naming convention is, I think I mentioned earlier, is everything, customer 10 is going to have the same naming conventions, VASI left 10, VRF 10, so on and so forth. And then the VASI right has the IPNAT inside statement. And so the VASI left and right are 2.0.0.1, 2.0.0.2. And we'll see that in the routing statements that are required so that we can route between the VASI interfaces, and that lets us communicate between the two VRFs. So the VRF 10 left is really communicating ultimately with the core router, and the VRF 10 right is really communicating, is in the context of the VPN tunnel and the internet-facing interface. And the cool thing is we can communicate between these two VRFs quite easily through the VASI interfaces. Okay, so I got the VASIs, and then this is just crypto policy, almost exact from previous videos that I have. Paste that in. Just doing the IKEv2 setup for this particular customer. So customer 10 is at their peer is 30.40.50.1. And then tunnel interface, we're on IP unnumbered, so I'm just kind of inheriting, I'm not setting an IP address for it, I'm just inheriting the IP address of gigabit Ethernet 2. And then this has the IPNAT outside statement as mentioned previously. So getting into the routing, the first route is going to be for the global table. So if I do show IP route after I put this route in, then basically it's saying if you want to get to 10.77.0.0/29, send that to the VASI left interface. So now we talked about this 10.77.0.0/24 network. This is the first instance where I've chopped that up into a /29, and I've assigned it specifically to the customer 10 tunnel by routing it to the VASI left 10 interface. And then everything else, there's not going to be any other references to any of this in the global routing table. Everything else after this is all within these VRFs and completely isolated on a per customer or per tunnel basis. So now we're going to put in the routes for the VRF 10 left. So what's happening here is I want to, basically this 10.77.0.0/29, it's going to get routed to the VASI right interface and then all the way up to the tunnel interface. And so this first statement is just saying to get to that network, the next hop is 2.0.0.2, which is VASI right, egress out of VASI left. The next statement is saying if I need to, for the return traffic, 150.2.3.0 network /24, then egress out of the gigabit 1 interface, which is here, and your next hop is 172.16.0.1, which is the core router. And then now we have 3 routes for the VRF 10 right. The first one is saying if, for the return traffic, so the idea here would be that the traffic has been decrypted. It's come into this tunnel interface over the IPsec tunnel. It's been decrypted, and it's in the context now of VRF 10 right, the packet is. So I need to be able to send that back ultimately to the core router in the 150.2.3. network. So it's saying to start doing that, egress the VASI right interface with next hop of 2.0.0.1, which is VASI left 10. The next route statement is basically saying to get to the customer network of 10.254.254.0/29, use the tunnel interface. So this is this is basically the only time you're going to see a route to the actual customer network. It's in the context of VRF 10 right, and it's hidden the tunnel interface. And when you do the NAT, the NAT on VASI right, IP NAT inside, tunnel interface, IP NAT outside, per the Cisco documentation, you do have to, I have to push that 1077 route all the way up so this NAT rule works correctly. So that's the third routing statement, is I've been pushing this 10.77 network all the way, initially to the VASI left, to the VASI right, and now I'm pushing it to the tunnel interface. And so these 2 routes that are specifying next hop being the tunnel interface, the 10.77 one is there basically so the natting will work, and the 10.254 is there because that's after NAT translation. That is the network that I need to send to over the tunnel. So basically, when I send from my side 10.77.0.2 destination IP gets translated to 10.254.254.2, and then I need a route that says, okay, well, I've got a packet with that destination IP. I've got to have a route that says to get to that network, use the tunnel interface, boom, then we're encrypting it and sending it over the tunnel. And then I need to put in that actual route statement, that actual NAT statement into the config. And that would complete the configuration for that specific customer tunnel. So if I ping 10.77.0.2, that works. And then what that's doing is routing to the VRF's router, and then it's getting encrypted on the VPN tunnel to customer 10, ultimately showing up at customer 10 Linux box here. So if I do sudo tcp dump -i eth0 host 150.2.3.248. So basically what's happening here is on the HQ Linux side, my source IP is 150.2.3.248. I'm sending to a NAT IP of 10.77.0.2. That's getting translated via this statement that we've talked about here, this particular NAT statement. And it's getting sent over the VPN tunnel. And we can see that now I'm on the customer 10 Linux, when I'm running the packet capture, indeed the traffic from the HQ Linux is what's showing up here. And I can do, like I can do a SSH Cisco at 10.77.0.2. And now I'm in a shell for that system. So you can see I logged into that through SSH. And now I'm back in the, the top level context of the shell for this HQ Linux. And we can see the SSH traffic in the packet capture. So there's the port 22 stuff. Okay. So basically, it's just going to be the same concept for the other customers here, just with, they have a different NAT range. And there's going to be a NAT translation associated with that. So now I'm going to start configuring the tunnel for customer 20. So I'm going to paste all the crypto information in for that. And then customer 20, their peer IP is 40.50.60.1. And then we need to do the VRF definitions and VASI interfaces. Same exact concept as the previous, but of course the VASI left 20 and right 20 are on different IPs, so 2.0.0.5 and 2.0.0.6. Tunnel interface, referencing IP unnumbered and the destination of the customer 20. And then we'll put in the single route that's associated with the global routing table. So then if I do show IP route for the global routing table, then we can see that if you want to, as stated earlier, 10.77.0.0/29, go to VASI left 10. 10.77.0.8/29, go to VASI left 20. And actually I didn't show the routing table, so we'll take one step back here. We'll do show IP route VRF 10 left. So this is just going to show the routing statements that we put in, like to get to that 10.77/29 in the context of VRF 10 left, send it to next hop 2.0.0.2, which is VASI right, egress VASI left 10. If we need to get back, the return traffic needs to get back to the core 150.2.3.0, send that out physical interface gigabit Ethernet 1 via 172.16.0.1, which is the core router. And we'll look at VRF 10 right. So we've got, if we need to get to the, we're pushing that 10.77.0.0/29 all the way to the tunnel interface as mentioned. And then to route the actual customer network, 10.254.254.0, send that also to the tunnel interface. And then for the return traffic to get back to the 150.2.3.0 in the context of VRF 10 right, Then next hop 2.0.0.1, which is VASI left 10, egress out VASI right 10. So getting back to the tunnel 20, then we're going to put in all the same type of routing statements and natting. So basically, covered all of this stuff, and notice that the NAT statement in this case is 10.77.0.10 maps to that same local IP that we had on customer 10. And so that's the point is, by having the isolated routing and using the NAT statements here, I can get to multiple systems at different customer sites over different tunnels that all have the same local IP space. So, so this is same exact concept of the previous, but now I'm using an example of 10.77.0.10 to get to the customer 20 Linux. So that's all in the configs now. So should be able to ping 10.77.0.10, which I get a reply as expected. That's going to customer 20 Linux box. So again, I'm on the HQ Linux. 10.77.0.10 is what I'm sending to. My source is 150.2.3.248, and on the packet capture we see that same exact concept of the previous one, and that's kind of the beauty of the isolated routing scenario here. So last but not least, start configuring the customer 30 tunnel. VASI interfaces for the customer 30 tunnel. Tunnel interface. And in this case, the peer for this customer 30 tunnel is 50.60.70.1. And same exact concepts for the routing and the NAT statement. So on this one, the NAT statement's going to be 10.77.0.18 going to that same local IP address. So now, so if I ping, let's do this. If I ping the .18, so that works. We'll see that pop up on the packet capture. And then the idea with this access list is basically saying, like, technically the tunnel, anything could come over the tunnel from the customer side. And basically what I want to do is I really only want to send anything out of this VRF's router if it's had one of these NAT translations happen. So what I'm doing then is, from the context of the physical interface G1 in the out or the egress direction, I'm just setting up an access list that's going to allow bidirectional traffic on SSH, port 80, port 443, but it's got to either have a source or a destination of this 10.77, and the same thing for allowing ping over ICMP or ping over the tunnel. So that way, like, the idea would be is if it hasn't, so if I, since this is it's on the G1 interface and it's on the out direction, basically if traffic comes over the tunnel and it didn't hit a NAT rule, it's not going to match this access list and it's going to get dropped. So just kind of a rudimentary way of filtering traffic and then only allowing stuff that's actually hit a NAT rule. So I'll paste that in, and I should continue. So we'll go back, ping the .2, still works, ping the .10, still works, and ping the .18, still works. So that's a pretty quick run through of what's going on here, but that's kind of the beauty of the isolated routing. So I have 3 different customers in this example, and then basically all I'm doing is just changing the naming conventions. So it's VRF 10 or VRF 20 or VRF 30, same thing with the VASI interfaces, the tunnel interfaces. And then again, taking what's a /24 network that the core will send. So if I go show IP route, I've basically assigned this 10.77.0.0/24 NAT space for my customer tunnels. If there's any traffic that has a destination IP in that network, send it to the VRF's router. And then from there, then I'm segmenting that /24. I'm saying I have 3 different customer tunnels, customer 10, customer 20, and 30 as referenced by these VASI interfaces. So I've got /29s for each one of those. So I could assign NAT IPs and do additional NAT translations isolated in these VRFs that are associated with these VASI interfaces. So again, that /24 network gets routed over to the VRFs. Then I can split that up into some /29s or whatever else. And then each one of these is the NAT range for that specific customer. It's completely isolated. And so if I do show run NAT or show run IP NAT, do show run include NAT. So we can see here that, the concept is in each one of these customer networks, I need to be able to get to the exact same IP space. They've got overlapping or exact IP space. Well, I have completely isolated routing for each one of those. So I have a NAT statement for this customer 10 tunnel in the context of VRF 10 right, NAT statement VRF 20 right, VRF 30 right, and that's what allows me to have 3 separate VPN tunnels to 3 different customers that are all using the exact same IP space. So yeah, that's pretty much it, and thanks for watching.